Hey, welcome back to Math with Patrick. Today is February 5th, and we're solving problem number 36 in this Daily Epsilon calendar. All right, we need to find the number of Mersenne primes less than 10,000. All right, well, just for a definition, a Mersenne prime is a prime number such that it follows the format of 2 to the power of n minus 1. And this n has to be a whole number. And we should just check some values of n and see if this number produces a prime. I think the usual notation is a big capital M with a subscript of n. And so I could try like big M of 1, seeing if this number is a Mersenne prime. I'll do 2 to the power of 1 minus 1. Well, 2 to the power of 1 is just 2. And then 2 minus 1 is 1. So this number 1 is not a prime number. The first prime number is 2. Just 1 isn't prime. So the first number to check when n equals 1 didn't give me a prime number. Okay, well, let's just try the second candidate number, m2. 2 squared minus 1, that is 4 minus 1, or 3, and aha, 3 is a prime number. So this search for primes by doing a power of 2 and subtracting a 1, this did get me a prime, 3. All right, well, let's just keep trying. M of 3 would be 2 cubed minus 1. That is 8 minus 1, which is 7. 7 is another prime number. All right, so far so good. I mean, I'll just keep trying it this way. I don't see anything wrong with it. Though, actually, hold on. There are some numbers that I don't actually need to check. And so let's do a little bit of an algebra proof right here. If that power of n is even, you could maybe think of me doing like 2 to the power of, I don't know, 2k. Just k is some integer, and that 2 just kind of shows that it's prime, or sorry, that it's even. If I do 2 to the k, or 2 to the power of 2k minus 1, this is a difference of squares. I have a square number here because I know that 2 to the k times 2 to the k gives me this number. And then I have 1 times 1 gives me this number. And I know that I can factor a difference of square numbers into, let's see, it would be 2 to the k plus 1 times 2 to the k minus 1. You could double check this if you decided to distribute out these two binomials. You're going to return back to this. So if my power is even, I can then split it up into two numbers and will therefore factor it and therefore show that this would be a composite number every time. Well, okay, not every time. Earlier, maybe you're saying like, oh, wait, Patrick, this was an even number and you did get a prime, and that is true. I guess if I plug in a 1 and a 1 here, then I will get 3 times 1. Okay, yeah, then that's prime. But just for the sake of example, maybe, I'm checking M sub 4 right now. That would mean K is 2. And then now I have a way to factor whatever number I get when I do 2 to the 4th minus 1. Let's see, okay, that would be 15. And then this factoring right here shows me that I can factor it into 2 squared plus 1 times 2 squared minus 1. Cool. 5 times 3 is 15. So I just wanted to do that. I was going to say real quick, but that took a little bit of time, just to show that we don't actually need to check any of these even numbers. And furthermore, I think there's actually a way to prove that we only actually need to check prime numbers as our power of 2, though I don't know. There's a way to prove it, but I don't know. I just didn't feel like that one. Anyways, I don't need to check the fourth number here because when it's even, I will have a way to factor it. So checking the fifth number, 2 to the 5 is, let's see, 8, 16, 32. Okay. If I subtract 1 from that, I get 31. And I've memorized enough primes to know that 31 is prime. Let's keep going. M with a 7 is 2 to the 7th minus 1. That'll be 32, 64, 128. That's 127. At this point, my memorization of primes has stopped. Actually, I think this one's prime, but I do need to check. Let's see, checking divisibility by 3. If I add the digits, then I get 10. 10 is not divisible by 3, and that shows me that 127 is not divisible by 3. It's not divisible by 5 because it doesn't end in a 0 or a 5. Let me do a little bit of long division to figure out if it's divisible by 7. Okay, and then yeah, 7 doesn't go into 57 evenly. I think it goes into 56 evenly. That's, 7 times 8. Okay, the division showed me that 7 isn't a factor. And then if I try 11, I know that 11 times 11 is 121. And then 11 times 12 is going to be too big. That's 132. Okay, and I've checked primes all the way up until 11, and none of them have worked so far. And there's like a trick here where if you're trying to, see what factors there are of a number, and you've checked all the primes so far and none of them have worked, if the next prime and you square it is bigger than your target number, you actually don't need to go any further. 11 was the last prime number that I needed to check. There's an earlier video where I do some factoring sometime in January, and I kind of go over why that squaring is a good method to show when you're done. So anyways, 13 is too big, and I checked all the primes from 2 to 11. None of them worked, and that shows that 127 is prime. Okay. M, the 9, that's 2 to the 9th minus 1. Earlier, like I said, I know that when this number is composite, this number is composite. Forget how to prove it. So I'll just figure out this number and find out its divisibility like normal. Let's see, 2 to the 9th. That's going to be, 128, 256, and then 512. 512 minus 1 is 511. And I'm pretty sure this is composite, but I'm not quite sure. And so I'll have to check all those numbers all over again. 2 doesn't work because it's odd. 3 doesn't work because the digits sum to 7. 5 doesn't work. Let's try long division with a 7. Let's see, 7 times 7 is 49. Ooh, nice. And then 7 goes into 21 evenly. That's 3 times. So this number right here is 7 times, wait, is that how it works? 7 times 73? Yeah, okay. And that shows that it's composite, and I have not found a Mersenne prime. So it's still a Mersenne number, kind of, because it's 2 to the power of something minus 1, but I was able to factor it, and so it is not a prime number. Got to keep going. Okay, 2 to the 10th minus 1. Yeah, that would give me a composite number because 10 was even. So let me check 11. 2 to the 11 minus 1. These numbers are getting real big, so checking for whether or not the number is prime is going to be a little bit harder moving forward. Let's see. 512 doubles to 1024. That doubles to 2048. Minus 1 is 2047. Okay. Got to check if this one is composite or prime. All right. 2 doesn't work. 2 plus 4 is 6. Plus 7 is 13. That doesn't work for 3s. 5 doesn't work. More long division with the 7. Let's see if 7 is a factor of 2047. Goes into 20 twice. It's 14. Subtract, bring down. 7 times 9 is 63. Subtract, bring it down. Dang it. Okay, well, 7 doesn't go into 17 evenly, so 7 is not a factor. Earlier in my series, I created a prime checking function, and I'm really tempted to just go ask the robot whether or not this number is prime. In that previous video, I discussed how it gets computationally harder to check whether bigger and bigger numbers are prime. And this is kind of showing you why this is the case. How about here? I'll skip until I find the next prime number, or whether or not prime numbers work for 2047. Found it. It was 23. Let's see. The square root of 2047 is about 45. And so using this just kind of successive prime search, you would need to go up to 45 at the latest or the largest. But 23 was the first prime to work. Here, let's just do a little multiplication to show that that's the case. 3 times 9 is 27. 3 times 8 plus the 2 is 26. Placeholder 0 for the 20. 2 times 9 is 18. And 2 times 8 plus the 1 is 17. 7, 14, 10, 2. Carry the ones. There we go. So this shows that 2047 is composite because it has some factors that are not 1 or itself. Okay. Fortunately, our search is capped, as in these Mersenne primes can't be greater than 10,000. So M13, so the 13th Mersenne number to check whether or not it's prime, will be 2 to the 13 minus 1. Let's see, 2048 doubles to, 4,096. And then doubling that again, I get 8,192. So 8,191 is the final number that I need to check whether or not it's prime. And based on the problem statement, and also knowing that today's date is the answer, apparently this number is prime. You'd have to, by hand, check up to the square root of 8,191. I don't really know what that is off the top of my head. Like, gosh, I don't know. Is it 60? I mean, no, bigger than that. 70, 80. Oh, about 90. Yeah, because 90 times 90 is 8,100. And so you'd have to, if you're doing this by hand, check primes from 2, 3, 5, 7, all the way up until a prime around 90. So like maybe 91 or something around there. That's a lot of primes to do by hand. So at this point, honestly, either just Google it, really, or you could do it with a calculator too. You could find a list of primes and then try doing 8,191 divided by 2, divided by 3, divided by 5. And if you just keep checking all the primes, assuming that you will see that you only get decimal numbers as your quotient or your result there. So let's just Google it together, honestly. Is 8,191 prime? Yep. Cool. That's all. Alrighty, so let's go back to the document. Well, this number is prime, and counting all of the Mersenne primes that I found, there's 1, 2, 3, 4, 5 less than 10,000. And that's today's date. So, all done with this problem. Thanks for coming along. And yeah, I'll see you tomorrow. I'll see you in the next video. All right. Bye-bye.